certain amount of time. So once the valves on either side of the filter have been opened, then you can then go on to your water source, turn on the flow. That will then start to process through our filter here. And basically this filter is a hollow fiber filter, which means it's a bundle of straws, if you will, that have all been packaged together in this epoxy matrix. And anything that is under 30,000 Daltons is going to pass through that filter, but pretty much any microorganism, a virus, bacteria, protozoa, as well as some larger proteins will be trapped simultaneously within this one filter. So as all of the salts and water are just flowing back through the other end of the filter, you'll notice that you start to see the total volume of the water that has been processed through the filter starting to increase, so that you can determine if this is a very clean water, such as we did with the aquifer. 500 liters of water we were suspecting was probably going to be required in order to get anything detectable. If you're using a very dirty water, such as some of the rivers that we've gone to, we typically do 100 because that's a good log scale up from the standard technology, but you can do a much lesser volume if you have a very, very dirty water, like a wastewater, per se. So once you are happy with the amount of fluid that you have collected, you can just simply cut off the flow, tell the computer that yes, I am ready to go back to the lab to do the recovery portion of the demonstration today, where you will then be able to remove the organisms back from that filter. So it will start to turn off the flow meter, turn off the pressure transducers electronically, and then all of the valves will then close back up to keep all of the organisms trapped within that filter encased within the filter, so you don't have any loss, there's no aerosol generation. So that you can then just transport back to the laboratory. So at that point, we will step over to our second unit here. And now we would have reattached the top portion of the unit, which contains the pump that will actually be utilized to flow the buffer into the filter that will be utilized to recover our concentrated sample. And our units actually function in a different way than a lot of other groups use ultrafiltration. We were the first group to actually use dead-end ultrafiltration, which means that we are single passing the fluid through the filter instead of the recirculated mode that a lot of the CDC and EPA labs have used in the past. What that allowed us to do was to make this much more simple, much simpler, much more portable. You don't have to have a collection reservoir to recircle that fluid through that the tangential methodologies require. So once you have come back to the lab, reattach the recovery portion of the unit, you can then tell the computer that yes, I am ready to recover my sample. And the first thing you are going to hear is that this metering pump will be activated again based on a program that the software is communicating to the device that will replace whatever remaining sample fluid from the river, from the drinking water that may have residual chlorine left in it. We're going to replace that fluid with our buffer solution that our sample will then be contained in to stabilize the organisms and to increase the concentration of our sample. Again, basically dewatering the sample. So we're taking all of the particulates in 100 liters and squishing them down to something in about the 400 milliliter level. So again, the valves will open in a certain timing. We will then activate the pump, and it's going to whine just a little bit. And so basically, again, what that's doing is just drawing the buffer fluid up into the unit and pushing it up through those same fibers that our sample was collected. And then once the proper amount of fluid has been delivered to the pump, the software again will tell the pump to stop. We will have a small incubation period where that fluid is being interacted with the fibers and the organisms to dissociate them from those filter fibers so that we get the best recovery that we could possibly get from these organisms. And we typically get upwards of 90% of all the different grades of microorganisms that we have tested. So our recovery efficiency is very, very good. The intra-filter variability is worse than the inter-laboratory personnel variability, because this is all software controlled, is much, much tighter than you would see, again, through a more manual system that I know they had actually done some round-robin testing for the tangential systems in the U.S. several years ago, and that the variability between final sample volume was much broader. We might see 5 to 10 milliliter difference between personnel and between sample type. So once the incubation has begun, again, the computer will take the timing and monitor how long. We have a certain process that we've developed here that has worked fairly well, again, across a variety of sample types. That once the incubation has been completed, and again, this is on a little tighter scale for the demonstration purposes today, the fluid that was incubated will then be removed from the filter, and again, this is part of our patent pending concept here. This next portion of the process, that the extra fluid will then be, again, removed from that filter. And once that has been done, then you will be alerted by the software that, yes, it is time to recover our sample. So we're just waiting for the system to catch up to where I've been talking about.
Yes. Is this the total amount of time that it takes? The time that we're doing right now in this demo?
Typically for collection, it's about 35 minutes for a 100-liter sample. For recovery of the sample, we have about a 10-minute incubation time that we allow that fluid, again, to interact with the organisms against those fiber walls to increase our recovery. But the total active time that you're involved in the recovery process may be 5 minutes. Maybe.
So the whole thing together, though, is going to be an hour?
Yes, ma'am, and that includes transport, getting it out of the car, back in the car, and actually all of the platform, the computer, as well as some of the other transport carts actually fit in the trunk of our graduate student's car. You have a what kind of car again? A Nissan Altima. So it doesn't take up a whole lot of space. It's easy to transport around. So again, what you're hearing now, again, is the additional fluid that will actually now be part of our sample. Again, being pumped in the reverse direction. Since this is a dead-end system, and again, this is part of our patent pending process here. We are now going to go in the opposite direction from collection. So the fluid is being pushed in the exact opposite manner that it was collected, so that all of those particulates that have been locked on the insides of those straws are now being kind of like a spitball in a straw. You're just going to push those back out the bottom of the straw, and you can see what.
And that's from the tap water.
Oh, no,
this is from a
different sample.
But that is actually not. We have actually done some samples.
That's not from the tap water.
That's
no.
I was going to say. I'm wondering.
So actually, there may have been some pictures if you were interested somewhere else in the lab where you can actually see the difference in the color from a beach water, from drinking water, river waters, that the cooling towers. That there's a marked color difference. The turbidities are increased by several hundred, if not thousands of fold. But we have done a lot of work also in the sample processing arena for the detection portion of, we've done everything from culture to PCR and proteomics on samples.
So where did that sample actually come from?
It was more turbid sample that had a lot of soda particulates and stuff.
Okay, not from a river or any particular place?
It would be most similar to a river. We were testing on a new process. So
okay.
This is the backflush big time.
So yeah, that actually is fairly reminiscent of a lot of the waters and rivers from Florida.
And one thing I studied in